Hello everyone. What I'm going to do in this lecture is to give a general solution to this uh, system of first order ODEs that we derived in the previous lecture. So if you remember, we started with an nth order ODE and then we converted that into a system of first order linear ODEs, which is shown here. The x and x equals to ax plus bt, where a is a n by n matrix and x is the vector of unknowns that we want to know, and bt contains the non-homogeneous term of the ODE. Okay, so now I want to give a solution to this. So let's get started. So what is the general solution of this? So the general solution is basically similar to first order ODEs that we solved before, and that is xt, which is now in a matrix form, equals to the homogeneous solution of this plus a particular solution. So let's find each of these solutions separately. So let's first start with the homogeneous solution. Homogeneous solution. Okay, like this. Okay, what is the homogeneous solution? So the homogeneous solution is when my bt here is 0. So let me just set that to 0. Then I need to solve this equation. Basically, dx dt equals to, and this is my homogeneous, so I write it as axh equals to ax homogeneous. Ax homogeneous. Okay, so here we assume, similar to the previous one again, that we solved in the first order ODEs. You can actually solve something like that for each of the equations and get a matrix form, like here. Or simply what I'm going to do is as follows. I will do it another way. So I assume an exponential solution in the form of xh t equals to V is a matrix e to the lambda t. Okay, so I assume it has a exponential solution in this form. It's kind of also we know that the previous one also had a exponential solution in a just first order when we talked about the first order linear ODEs. And what is lambda here? Lambda is basically scalar, and v is a Rn vector. Okay, now we assume this solution and then we substitute it back to see whether it works. So let's see. If I substitute this back, I have d over dt of v e to the lambda t equals to, what would be the derivative of this? Let's first calculate the derivative of this. So the derivative of this would be with respect to t, and the only function that has t here is e. So, and the derivative of that would be lambda. So lambda times v e to the lambda t equals to, and what is this? this is basically, if you see that, and this is the left hand side, equals to my right hand side. What is my right hand side? It is AXH. So it should equal to AXH, which is, in this case, A times V times e to the lambda t. Okay, so now this is the left hand side, that is, and also the right hand side. In both of them you have e to the lambda t, which cancels out, so I can just cancel this out. Do it with this. These two cancel out. So what do I get here? I get a very interesting formula, and that is, if I assume this, A V equals to lambda V. So it's very interesting. Now we get back to an eigenvalue equation. Okay, so we get back to this eigenvalue equation, and so lambda must be an eigenvalue of A and V is its eigenvector. Okay, so lambda 1, lambda 2, up to lambda n, and V1, V2, Vn, they are linearly independent E vectors, and all of these form the general solution of this homogeneous solution. Okay, so the general solution of this homogeneous solution, so I will just write the homogeneous solution of the whole system. Which is what? Which would be XH T equals to sigma I equals to 1 to n Ci Vi, the eigenvector, e to the lambda I t. Okay, very, very important. So now, if this A that we had, if this A that we got is we can diagonalize it. So if A diagonalizable, then what can I write? I can say that AP equals to P times lambda 1 all in the diagonal, lambda n, these are 0, where P is basically my eigenvectors, V1 stacked together, V2 and Vn. Okay? So if I want to write it this way, so we have AV equals to lambda V for each eigenvector. I can now show it as a for all of them. If I want to just show it as a matrix form, it would look like something like this. So here I can say that, and I call this D. A equals to P times D. If I multiply it by P to the minus 1, then I get A times I, and then I get P times D times P to the minus 1. So now if I make the exponential of this, I will get e to the AT equals to P e to the dt P to the minus 1, where e to the dt is basically the same matrix, but we have all the exponential terms, e to the lambda nt. Okay? So in other words, if I want to write this sum in a matrix form, my homogeneous solution would be e to the AT times C. Okay, just C is my constants of integration, which is a Rn vector. Okay, so let me. This would be an Rn vector. And so this is a matrix representation of this, okay? Of my solution, homogeneous solution. And similarly, for particular solution, what we can do is a similar trick. Now, let's do that. So particular solution. So for particular solution, my XP would be, if you look at if you go back to first order linear ODEs, how we got that and what was the particular solution, I can just use that and just rewrite it here. So if you remember what was that, we can do the same thing here. So it will be the integral of T0 to T e to the A T minus S F S ds. Okay, so it would be something like this for particular solution, and then my general solution, if I want to say for this system of linear equations, would be e to the A T times C, which depends on your initial conditions, plus the integral from T0 to T e to the a t minus s f s d s. Okay, so this would be my general solution for this equation, okay, for this linear system of equation. And this is very interesting because now you can solve any nth order ODE with very similar and simple way. So you have this nth order ODE, and we converted it into a system of linear ODEs, and then we can simply solve it with this general solution that is shown here. Once we find that A matrix, once we find this A matrix, then we can simply find what this A matrix here. We can simply find a homogeneous solution here, e to the a times t times c, where e to the at is basically this p times d e to the dt times p minus 1, and p is just the eigenvectors of this system. So this is basically my e to the at. And after that, you can simply also calculate this the right integral to get the, based on the a particular solution, to get the non-homogeneous part of your solution. Okay, so now let's solve one example of this. This is very general, and now you can use it for any given nth order ODE. So let's solve one example to see how we can actually use that. So solve the following second order ODE. And my ODE as follows: d square y over dt square plus 3 dy dt plus 2y equals to sine of t, with y at 0 is 0, and the first derivative dy at dt at 0 is also 0. So these are my initial conditions. Okay, now let's solve this. So first, what I want to do, I want to use this technique. There might be other techniques when you have higher order ODEs, like second order, especially for second order, we also have many other techniques. But I want to use this specific technique that I talked about. So first, convert to a system of first order ODEs. So first we convert this to a system of first order ODEs. So to do so, I will write xy, x1 is y, and x2 is dy over dt. So this gives me the x1 over dt is basically x2. Let me just write it. It's going to be dy dt, which is basically x2. And this one, the x2 over dt, would be d square y over dt square, which from my original equation here, just look at it here, it would be minus 3 dy over dt, which is basically x2, minus 2 times y, which is x1, plus sine of t. Okay, so let's constitute our matrix that we had in a matrix form. So this gives me d over dt, just two equations now instead of one equation. One second order equation, I will have two first order equations. x2 equals to 0, 1, minus 2, minus 3, x1, x2, plus 0 and sine of t. Okay, and my initial conditions, x at 0 would be 0 and 0. Both x1, which is y, and x2, which is dy dt, would be 0. Okay, so now I have my system of linear ODEs that I constructed, and now this would be my A, right? And this is my X, and that is my, if I go here, A and B, right? A, X, and B. Okay, so this is my A, this is my X, and this is my BT matrix. Okay, so the general solution here, I know it's going to be e to the a t times c. Okay, this is my general solution. But in order to find that, I need to find these P matrix and also both the lambdas and also P, which is basically eigenvalues and eigenvectors of this matrix. So I need to find those eigenvalues and eigenvectors. So first we find eigenvalues. And to do so, I simply calculate determinant of A minus lambda I equals to 0. So the determinant of this 2 by 2 matrix is going to be minus lambda, 0 minus lambda, 1 minus 2 minus 3 minus lambda equals to 0. So this gives me lambda times 3 plus lambda equals to minus 2, right? So my lambda 1 would be minus 1, and my lambda 2 here, from here I can see, would be minus 2. Okay, so I found these two lambdas, which are my eigen values, right? And you can check it here too. If you put minus 1, it's going to be 1 here, and then it's going to be minus 3 plus 1, minus 3 plus 1, which would be minus 2. So minus 2 times 1, yes, minus 2. Yeah, that's correct. Okay. So I found now eigenvalues. Now I need to find my eigenvectors. So that is my second thing that I will do. So eigenvectors. So this is eigenvalues, then I have eigenvectors. So for eigenvectors, let's find it first for the first one. Lambda 1 equals to minus 1. So we need to solve I We need to solve. A plus I times 1 times V equals to 0. Basically bring that lambda 1 to the left hand side, and here my lambda is minus 1, so it becomes a positive value. So then I get 1 1. My A, just you need to add 1 to the identity matrix to that, so it would be minus 2 minus 2. V1 V2 equals to 0. So this gives me V1 equals to minus V2. So one set that I can choose is maybe I can just say here it's Y, so we don't no, actually another name. Don't want you to confuse this, so we can name this as, let's say, M1, M2. So this gives me M1 equals to minus M2. So my V1, my first eigenvector here would be, I can choose 1 and minus 1. Okay. So for lambda 2, the second one is lambda 2 equals to minus 2. And for this one, you can write it down, and what you will get is as follows. V1 equals to, let me just write. M1 equals to minus 0.5 M2. So V2 would be minus 1 and 2. Okay? Now, so now that we got this, I can constitute my P matrix, which was basically the stack of these two eigenvectors. So it's going to be first V1, which is 1 and minus 1, and then second is V2, which is minus 1 and 2. And I also need to calculate its, in order to create and to write this e to the AT, I also need to calculate its inverse matrix. So I will just write it down. What would be the inverse matrix? Just this times that matrix would be I, so I can find the inverse matrix of that. So I will just write the final answer here, which would be 2, 1, 1, 1. Okay. So based on this, I can calculate e to the AT matrix, which is basically P times e to the minus 1t, because this is my first lambda t, 0, 0, and my second eigenvalue is minus 2 times p to the minus 1. Okay, so this gives me that matrix of e to the AT. Okay, so now if I substitute this, I will get my homogeneous solution would be, and you can calculate it. It's basically, I have C e to the AT times C So it would be C1 e to the minus t plus C2 e to the minus 2t. Okay. Now, the next thing I need to do is to calculate the particular solution. So I found the homogeneous solution. So for the particular solution, I need to calculate this integral from 0 to t of e to the a t minus s sine of s ds. Okay, so you can calculate this integral. I'm not going to do that. And then what you will get is as follows. This would be our general solution. And there is another way to do this. I will talk about that. But our general solution would be this: C1 e to the minus t plus C2 e to the minus 2t plus my particular solution would be 1 over 10 sine of t minus 3 over 10 cosine of t. Okay, so my homogeneous solution and also particular solution. Now, there is an easier way in this particular problem. This was very general, so you can solve this for any problem that you have. But there is a simpler way to solve this as well for the particular solution, and that is you can also use other methods to guess this, like undeterminate undetermined coefficients and guess yp equals to a sine t plus b cosine t, because this is a sinusoidal function. That our non-homogeneous part is a sinusoidal function, so we can use other methods like undetermined coefficients and guess that our solution should also have a sinusoidal shape or sinusoidal form. So yp would be should be something like a sine t plus b cosine t, and then we can just substitute that into our original ODE here, and then find the particular solution, which will give us again this one. Okay, so it will give us this way. Okay, so this is another way to find the particular solution. Okay, now let's apply the initial conditions to find what are these C1 and C2, and that will complete our journey here to find the solution to this second order linear ODE. So apply initial conditions to find C1 and C2. So we know that y at 0 is 0. And what would be y at 0 here? So we have C1 plus C2. Sine of 0 is 0, so it's 0 plus 0 minus 3/10 equals to 0. So this gives me C1 plus C2 is 3/10. And my second initial condition was dy over dt at 0 is 0. And what would be my dy over dt? The first term is minus 1 times C1. So minus C1. The second one is minus 2 C2. And then the third one would be cosine, so plus 110. And the fourth one would be minus 3/10 times minus sine of 0, which is 0. So this whole thing would be 0. And this gives me C1 plus 2C2 equals to 110. Right? So now I have two equations here to find C1 and C2. Two equations and two unknowns. And if you solve it, you will get C2 should be minus 2/10. And C1, if you just subtract these two from each other, you will get C2 very simply. And then C1 should be 5/10. So my general solution would be as follows for this problem. YT analytical solution is 5/10 e to the minus t minus 2/10 e to the minus 2t plus 1/10 sine t minus 3/10 cosine t. Okay, so this is very interesting now. So this would be my final solution to this ODE. Okay, so let's review what we did in this lecture and just talk a little bit in general about this ODEs and what we found. So what the first thing we did is we said from previous lecture that we can actually, if you have an nth order ODE like this, we can convert it to a system of first order ODEs by introducing new variables, let's say x, and then I can show the whole system as this dx over dt equals to ax plus bt, which consists of all first order ODEs that I have solution for, that I had actually solved this before. So in this lecture, we started to give some general solution, and similar to first order ODEs, this has a homogeneous solution, a particular solution. So for the homogeneous solution, we just have dx over dh equals to ax and bt is 0. So I will solve for this. And in order to solve this, I assume that x, the matrix X has a expression in this form v to the e to the lambda t, and then when I solve it and substitute it back, I got a very nice property which gave me back actually the eigenvalue equation. So I found that the homogeneous solution would be just the sum of all eigenvalues, eigenvectors, and times the e to the lambda I t, where lambda is basically my eigenvalues. And this will form the basis of my general solution for this nth order system. Now, if A is I can diagonalize it. Then I can create this matrix and show it in a matrix form as e to the at, where e to the at is p times e to the dt times p to the minus 1, and this gives me a matrix form of this homogeneous solution. And the particular solution simply similar to my first order ODEs that I had found before here, yp is going to be e to the a times t to the minus s times fs times ds, and this gives me my general solution. And after that, we solved an example of this with a second order ODE, which is shown here. We first converted this to a system of first order ODEs. We found the eigenvalues, and we found the eigenvectors. We constitute this solution to give us the homogeneous solution, and this gave us C1 times e to the minus t plus C2 times minus E2. And then the particular solution, we have to get this integral, or another way you can do is basically just to use a method of undetermined coefficients and guess the sign. This, because the right hand side was a sine function, this should be also a sine function, and then we apply the initial conditions to get the final homogeneous solution. Okay, this was the brief introduction over ODEs, and from next lecture we will start on partial differential equations. Thank you very much, everyone.